So now the very important application of this projection is the least square fitting of the data. So this is a regression line, regression fitting line. Suppose we do series of experiments, right, and expect the output B to be linear function of the t. So this is what you can assume, that this is y, this is x. Right? Sorry, this is y, output is y, this is input is x. So that's what you can try to relate here. So this is y equal to, you can read as y equal to c plus mx. So that is the our generally we say that y equal to mx plus c. So that is out. I have, but for the sake of simplicity, I have represented b equal to c plus dt. I have given. Then suppose the observations are noted as T1, B1, T2, B2, Tm. So these are points. These are the points from the experiments. And now what I have to do is that I will fit I will represent this one in the form of a line, that is C plus dt1 equal to b1, C plus dt2 equal to b2. So I will represent them in the form of a matrix again. So what I do is that, because here this is constant, the value is 1, and I take t1 here, then I take a b1 here, and I represent these c and d unknowns here at this point. So this gives an ax equal to b form representation. So these are some of the points. I have represented them in the form of, this is okay, these are the unknowns, these are all the points, right? This is the output value, these are the input value, and now you can see ax equal to b representation. So what is the solution for this particular problem? So the best solution is approximate c, that is c cap, and d cap is the x cap that minimizes the squared error e square. So now what I am trying to do is that I am trying to fit a regression line, fit a line, right, least square line onto the points. So these are some of the points which you can see here, and now I am trying to fit a regression line through this particular point. And what will be the best best line? The best line would be that x cap that minimizes the squared error. We'll try to see that. What is this error? This error is represented as b minus. What is b? B is the actual output, right? B is the actual value, but whereas this is the predicted value. So now the output value minus the predicted value, you can see here, this is the actual value and this is a predicted value. So this will give the error here, and these errors, right, it will be if you try to add all these errors, the minimum, right, the minimum error which we get is the point, right, is the c is this the best c and d value, right, the best c and d value. So vector p equal to ax cap is close to b. On the graph, the error are vertical distances b minus c dt to the straight line, okay, not the perpendicular. So that means that this is not perpendicular distances, but we are interested in finding straight distance. This is the distance, okay, parallel to y-axis. That's what we are interested in, okay. And now let us take three measurements, that is b1, b2 and b3, right? So these are 3 points which I am taken. B1 is 1, and here t value is -1, here it is 1, t is 1, and b2 is -1, so t is 2, b3 is this, right? So now I have to fit a regression line. I have to fit a line in between these 3 points. So how will I do that? Suppose, so I'll fit one line here, and then, so what can I tell here is that, see, I have drawn a line here, but in practical, there are infinite lines which can be fit between these 3 points, right? So we have to start, right? We have to calculate the error and then try to fit the best line. So that is the idea here. So now what I do is that I try to project every point onto the line which I am trying to fit it. Okay, so in this case, B1 is projected here, and this green point, you can see that this is the projection value, and it is, the error is represented as E1. Similarly, here B2 is projected and the error is represented as E2. Similarly, E3. And what I do is that Ax equal to B right? Ax equal to b notation, I will try to represent them. C minus dt equal to 1, C plus dt equal to 1, C plus 2. So this is the point representation in the matrix form. So the matrix form, this will be represented as 1, 1, 1, minus 1. So now you represent 1, 1, 1 here, minus 1, 1 and 2 from here, and then C and D are unknown, and these are the B values which is brought here. So now you try to solve these equations, and then you try to get the, okay. So now if Ax equal to B, right? So this is in the form Ax equal to B, right? Ax equal to B. So if Ax equal to B, if this can be solved, then there would be no error. Okay. So that means the points are lying on the, whatever the points which you are trying to fit, all of them are lying on to the line which you are trying to fit it. So then there would be no error. But they can't be, as the points are not on the line. So here it cannot be. There is an error. So they are solved by the least squares. So now how to solve using the least square? That is, I multiply with A transpose, right? So now you can see that this is a rectangular matrix again. So rectangular matrix. So now to make it a square matrix, I will multiply A transpose on both the sides, and then you can see here I get a very beautiful square matrix here, and then try to simplify this. I will get two equations, try to solve them, and the best solution C and D I am going to get is 9 by 7, 4 by 7, I get it, and the best line that fits with minimum error is the 9 by 7 plus 4 by 9 by 7 plus 4 by 7 T, right? So now you can see that what are the projection values. So projection values, I know that E equal to B minus P is given. So I can find, I know the error, and I know the B value, I can find the P. So P1 is 5 by 7, P2 is 13 by 7, P3 is 17 by 7. So here I have shown, you can see here, I have shown this in the plane that these are the projections, okay, these projection values. And now we can see that how did we, yeah, so here in this case, how did we get P here? So P is equals to B minus E, right? So now I have shown here just to, yes. So now in the previous slide, we got the C cap and D cap as 9 by 7, 4 by 7. So the best line was represented by 9 by 7, 4 by 7 T. So now the line 9 by 7 plus 4 by 7 T has a height. So height is the projection value. So so the projection value, you simply substitute, yeah. So the projection value is 5 by 7, 13 by 7, 17 by 7. So you try to get the P values here. At the measurements minus 1, 1 and 1. You substitute this one in this equation. T values in this equation, you would get this height, right? That is the P value. So subtracting P from B, right? We already got B, and subtract from P, then we'll get the errors. So these are the errors, and we know that this is the minimum error. So this is the minimum error. Now the error follows the quadratic curve, right? So it follows the quadratic curve. So I hope that this minimum error would be this point, right? E is the minimum error that is happening at this particular point, right? So this is the least square fitting of data. Now that was the algebraic way of solving the problem. Now let us see the calculus way of solving the same problem. So what happens is that in calculus, what I do is that I try to minimize the error. So error is represented as B1 E equal to B minus AX whole square, and now B1 minus C minus DT1. So this is the actual value, and this is a predicted value. We get the error, and we try to square them. When we try to square them, we'll get two equations again, right? So what we try to do, that we try to in order to minimize, we have to take the partial derivative, right? So we have to take the partial derivative with respect to C and with respect to D and equate to 0. So in this equation, when we try to take the derivative with respect to C and D, you will get one equation with respect to C. With respect to D, you get one more equation that is equated to 0, and then we can solve these two to get the best, that is C cap and D cap, and the best line is shown here. The best line you will get in this way. The calculus way also, you will get the same line. And now least square, yeah. So find a quadratic equation. Yeah. So this is another problem where I am trying to fit a quadratic equation through this particular points. So quadratic equation through these 3 points. So the quadratic equation is represented by the formula ct plus dt square equal to y, which passes through the origin. So constant term is 0 in this particular case. So now what I'll do is that I will put x equal to t and x equal to t square. What I'll do is that I will try to get the value 1, 2 and -1. So this is 1 here. So this is 2 here and this is -1 here. What I do is that I try to square this one. I need t square, right? I need this t square. So x equal to t square, and then I get this 142 value, right? And now what is this x cap? X cap is c and d, which are unknowns. What is b? B is given here. B is 1, 5 and -2 is been brought from here. You can see, right? Yeah, so 5 is here and -2 is here, right? So you can see this. I'll erase this just for okay. So now my A is ready, X cap is there, and B is ready. So now we can solve the we try to solve using Ax cap equal to B, but we know that we cannot solve because it is not, the lines are the line which we are trying to draw is not passing through all the points. So that is why we cannot solve this. So what we do is that we try to multiply. Okay, we multiply by A transpose A, into x cap, and then it into A transpose B. So this is the formula we try to use and try to solve this. So we get A transpose A like this, A transpose B as 13 and 9. So now we try to equate now. So x cap is C and D here, and we get two equations. So the C and D values are D is -5 by 2 and 11 by 2. The equation for the quadratic equation is 11 by 12t minus 5 by 2t square. So this is the quadratic line which is fit, okay, for these 3 points.